So today we're going to talk about probability and the probability of multiple events. First, experimental probability means the probability of an event is the number of times the event occurs over the number of trials. For example, flipping a coin, you have a heads and a tails, so that's the number of trials would be 2, and the number of times the event occurs would be 1, because you can only flip a head once or a tails once. The probability of an impossible event is 0. The probability of a certain event is 1. Otherwise, it's a number between 0 and 1 or 0 to 100%. So looking at the first example, of 60 vehicles in a teacher's parking lot today, 15 are pickup trucks. So what is the experimental probability that a vehicle in the lot is a pickup truck? That would be 15 out of the 60 or 25%. Now try the U-Try and pause the screen for a few seconds. You should have gotten 60% or 30 out of 50. If a softball player hits 20 of her last 50 times at bat, that means she will not get a hit 30 times out of the 50, so that's 60%. Then the set of all possible outcomes to an experiment or activity is called a sample space. When each outcome has the same chance of occurring, it's called equally likely. An example of this would be flipping a coin, rolling a dice, as long as it's not weighted. Example 2. What is the theoretical probability of getting a 5 on one roll of a standard number cube? There is 1 5 out of the 6 numbers, so that's 1 out of 6, or about 17%. The difference between experimental and theoretical probability: experimental is something you actually do. Theoretical is in the theory how it's supposed to average out. Question number 2, what is the theoretical probability of getting the sum of a 5 on one roll of 2 standard number cubes? So what you need to do is list out the possibilities of how to get a sum of 5. So that would be a 1 and 4, a 4 and 1, 2 and 3, 3 and 2. These are separate. Think of like a blue die and a green die, so they can have different numbers. This gives you 4 possibilities out of 36 because you have 6 on each cube, so 6 times 6 is 36, which would be about 11%. Now pause and try the U-Try. The U-Try asks, what is the theoretical probability of getting the sum that is an odd number, one roll, of 2 standard number cubes? Well, there are 36 options, and half of them are even, half of them are odd, making the theoretical probability 50. Again, will this probability actually occur as an experimental probability? Probably not. Theoretical is overall what should happen, not actually what does happen. In example 3, we're talking about a batter's strike zone and how it depends on the height and the stance of the batter. The taller the person, the higher the zone. What is the geometric probability that a baseball thrown at random within the batter's strike zone is 17 inches by 22-inch area will be a high inside strike, which is a 4x6 area. So what you're looking at is what's the probability that when someone throws a ball at the batter that it's going to hit this 4x6 area. Well, 4x6 area is 24 inches when you multiply. The 17 by 22, the entire area, is 374, which is about a 6% chance. Now take a moment and try the U-Try. In this case, the entire batter strike zone is 300 inches squared, whereas the high inside strike is 3x5, so that's 15. 15 out of 300 is 5%. The shorter the batter, the shorter the strike zone. To find the probability of 2 events occurring together, you have to decide whether one event affects the other, meaning the difference between independent and dependent events. Dependent means one depends on the other. It affects the sample space. It changes something about the problem. Whereas independent events, they do not interact with each other at all. So in example 4, we're determining, are they independent or dependent? So based off the wording, do they affect each other? In the first one, choosing a number tile from 12 tiles, and then spinning a spinner, these are independent events. Tiles and spinners have nothing to do with each other. Picking a card from a deck of 52, then not replacing it and picking another card. So when we start, we have 52 cards, but the second time we have only 51 cards. So that means it's dependent. The last one, you're flipping a coin once and get heads. You flip a coin a second time and get tails. Even though you're flipping the same exact coin, these are independent events because you have the same chance of getting a tails and a heads either time. Now take a moment and do the you try. The first one is dependent, the second is dependent, and the last is independent. The first one, you can't choose the same person twice, so that's dependent, and your sample space got smaller because you took a kid out of the class. The second one, you ate the M&M, so it changed the sample space. And the last one, a roll of a standard die, is independent of each other. You have equally likely chance of getting 1 through 6 both times. Next, if we are talking about multiple events and they are independent, then the probability of A and B happening at the same time is the probability of A times the probability of B. Likewise, the converse is also true. If the product of the probabilities equals the product of A and B happening, then that means they are independent events. And remember from Math 2, this little kind of capital N is a intersection. Example 5, we are spinning a spinner that is divided into red, green, and blue parts of equal sizes, so it's equally likely to get each color. Then you flip a coin so you have a heads or a tails. And we want to know the probability of getting green on the spinner and the coin landing on tails. So this is the probability of green and tails. The probability of green is 1/3. The probability of tails is 1/2. We multiply these two, and that gives us 1/6, or about 16%. The next problem talks about a desk drawer and different contents of this desk drawer. You have 5 red pens, 6 blue pens, 3 black pens, 24 silver paper clips, and 16 white paper clips. So lots of pens and paper clips. You want to pick a pen and a paper clip without looking, so you're not cheating, and see what's the probability that you get a blue pen and a white paper clip. Well, we have 6 blue pens out of our total of pens, which is 14, and we have 16 white paper clips out of a total of 40 paper clips. We want the probability of the blue pen and the white paper clip, so that's again 6 out of 14 times 16 out of 40, which again is about 17%. Next, we are rolling a standard number cube and spinning the spinner at the right. So here's this one. We want the probability that you roll a number less than 3. Well, numbers less than 3 on a standard number cube are 1 and 2, so you have 2 options out of the 6. And the spinner lands on a vowel. There's only one vowel on that spinner, the U, so that's 1 out of 4. So 2 out of 6 times 1 out of 4 is 8%, and we are rounding these to whole percents. Next, it gives you the probability of A and the probability of B, and asks, are these events independent? So remember our rule from the previous page, if the product of them individually equals the probability of their intersection, they are independent. So is 0.35 times 0.2 the same as 0.07? Yes, it is. So they are independent. Now pause and take a few moments to do the you tries. The first one is no. 0.4 times 0.28 is not 0.112. Does not equal 0.12, excuse me. The next one, we have getting a red marble. There are 3 red marbles out of the 15. And then a green marble are 12 out of 15, because remember it says you are replacing it. So the sample space does not change. You have an option of 15 marbles both times. So this is a 16% probability. The last one, we're flipping a coin 4 times, and the probability of getting a head 4 times in a row is the probability of getting a head and a head and a head and a head. So 4 heads total. So that would be 1/2 times itself 4 times, which is 1/16, or about 6%. If the events are dependent, that means the sample space changes the second go round, then the way we find the probability of A and B happening is the probability of A times the probability of B after A has already occurred. So we change the sample space in our second fraction. An example of this is Grant and Iris are going to get something from the snack cart. There are 6 bags of pretzels and 10 bags of chips. Grant selects a bag at random and so does Iris. What's the probability that Grant will get a bag of pretzels and Iris will get a bag of chips? Well, Grant picking first gives him 6 out of 16 because there are 6 pretzels and 10 chips, so 16 total. But then once he selected his bag, Iris only has 15 items to choose from, but because Grant chose a bag of pretzels, there's still 10 chips left. So 6 out of 16 times 10 out of 15 is about 25%. Then, from a class of 5 girls and 5 boys, so 10 total, two students are chosen randomly. The first student is a girl. What's the probability that the second will also be a girl? So 5 out of 10 would be the first because there are 5 girls out of 10 in the class. But because you've already chosen one girl, then your sample size goes to 9, but you only have 4 girls to choose from this time. So it's 5 out of 10 times 4 out of 9, which is 22%. Now take a few moments and try the 2 you try problems on the back. The first one is 14% because 10 out of 30 of the marbles are red, and then 12 out of 29 marbles are blue. You changed your sample size because you did not replace the original marble. Next, you are choosing from 8 cards. You want to know the probability where both cards are greater than 5. The only numbers bigger than 5 are 6, 7, and 8. So that would be 3 out of 8 and 2 out of 7 the second go round because, again, you did not replace it. So that is about 11%. If A and B are mutually exclusive, then the probability of them happening at the same time is 0. So that would be like you roll a number cube and you get a 2 and a 3. When you roll one cube, you can only get one number. So that's a mutually exclusive event. The probability of A or B would be probability of A plus B. So you could say, what's the probability of getting a 2 or a 3, which greatens your chances. In this example, student athletes at a high school can only participate in one sport. Most high schools aren't like that, but some are. During the fall season, 28% of athletes play basketball, 24% on the swim team. What's the probability that they can play both? Well, they can't play both because the school says they're only allowed to participate in one. But what's the probability that they play either one? You add them up, and that's 52%. Next, a number cube is rolled one time. What's the probability of getting a 2 and a 3? Not possible at all, so that's 0. What's the probability of getting a 2 or a 3? Well, in a number cube, 2 occurs once, 3 occurs once. So that's 1/6 plus 1/6, or 33%. If there are overlapping events, you still add because it's an or, but you have to subtract the overlap. So for example, if we're polling the class and we're talking about boys and girls and we break it down by the color of shirt that they have on, and you want to know the probability of picking a female or the probability of picking someone wearing green. You can't count the females that are wearing green twice. You're only allowed to count them once. So probability of A would be the probability of picking a female. Probability B would be picking someone wearing green, but then you would subtract out the females that are also wearing green. So we don't count them twice. So in this case, the first one, probability of rolling either an even number or a multiple of 3 on a standard number cube. There are 3 even numbers, 2, 4, and 6. There are 2 multiples of 3, 3 and 6, and then the 6 is the one that repeated, so we subtract it out. So 3 out of 6 represents our even, 2 out of 6 represents our multiples, and the minus 1 out of 6 is the overlap. This gives us 66%. In a math class, suppose 52% on a dog, 33% on a cat, 14% on a cat and dog. We cannot count these people that have both pets twice, so we add the individual, subtract the overlap, and have 71% of people own a cat or a dog. The next question we're not doing because I'm not there to poll the class. The last one is talking about getting a sum greater than 9 or an even amount. If you write out all your sums, there are only 6 of these that are bigger than 9, 18 or even, 4 of them are bigger than 9 or even, giving us 56%.